All right, today we want to solve this problem. This is a half cylinder and it is resting on this surface with some friction. And then we apply this force. We want to find alpha in terms of the force and the other geometric values. And then we want to see at the minimum value of mu s, the static friction coefficient, such that there is no sliding or there is no slipping at the bottom. All right, so I around this O, the center is 1/2 of mr squared, and that is sort of expected because the whole cylinder would have mr squared, and then this is just half of that. So the effect of it around that would be half mr squared. And OG, this is center of mass, this OG would be 4r over 3 pi, and r is the radius of this cylinder. All right, so in these problems, kinetics problem, the first step would be to draw free body diagram. So we free it from the surround and we see what is the effect of outside to this. So we free that from the rest of it. So it would be this surface can apply two forces, friction and the normal force. There is no torque can be applied by this surface. Then we would have gravity. And then we have that external force F. So I think just for the simplicity of the formula, let's call this R, small r. So our formulas become simpler. Uh, so now, and the other thing that we need later, we have I around O, and that was sort of, expected 1/2 of mr squared. But if we want to I around G, then we can use parallel axis theorem. I around any point other than center of mass, we can write it as Ig plus m total mass times that distance. This is parallel axis theorem. So it is plus mr squared. So we can say that, okay, Ig would be IO, which is 1/2 of mr squared minus m that r squared. So 16 r squared over 9 pi squared. But we use Ig. So instead of this, which we can factor out mr squared would be mr squared times 1/2 minus 16 over 9 pi squared. We can use just Ig instead of this. So now let's write the equations of motion for this one. So we would have, for the x direction, we would have Ff equals max. And this acceleration is acceleration of center of mass. Don't forget that we are not dealing with point mass. We are dealing with a rigid body. Each point might have different acceleration. So when we talk about acceleration, it doesn't have any meaning unless we talk about acceleration of which point. And it happens that we can prove that we can write this sigma fx equals to max, and that ax should be acceleration of the center of mass, no other point. Acceleration of the center of mass in the x direction. So ff equals to acceleration of that point in the x direction, and this is the only force that we have in the x direction. Then in the y direction, we have n minus mg minus f equals to may. And then for the Euler's law of motion, I have another video on that. So we can pick 3 points. So for this sigma f, the center of mass, for Euler's law of motion, sigma t equals to I alpha, we have 3 options: center of mass, stationary point, or a point with acceleration that is 0. So it might have constant velocity, but most of the time we encounter a point that it is stationary, like a pin on a bar. So center of mass, stationary point, and there is one other point that you, I mean, rarely see, and that is the point that its coordinate vector to the center of mass is parallel to its acceleration. You can watch that video, but we rarely use that. So let's say just mostly 2 points, center of mass and a stationary point. So for this case, it would be center of mass. Now, I would consider this direction positive for alpha, because then I can relate acceleration of that and say that it is just r alpha in the I direction. And we can write torques in that direction, that positive direction that we just defined. So moments of the forces that are on that direction, it would be positive, and the rest are negative. Around center of mass, this mg passes through that. No moment. N passes through that at this moment. Not necessarily all the time, but at this moment, N also passes through that. Then we would have F times R minus FF times the distance, which is R minus small r, equals to I alpha. So now, if we look at this equation, let's, strategize before we dive deep and try to solve it. So the number of unknowns that we have, the number of variables that we have, FF, the friction force, is unknown. We don't know. We know F, this is what we apply. But this is one variable that we don't know. So 1, AX, 2, N, 3, then everything is 4, and then alpha, 5. So we have 5 variables, 5 unknowns, and we have 3 equations. So it's not enough. This is not enough. So this is the place that we use kinematics. These are kinetics equations that relates forces and accelerations and torques and angular acceleration. Now we see that these AX, AY, and alpha cannot be free, all of them. They are related due to the geometry of this half cylinder. So let's find that from kinematics. So acceleration of this point O, let's use the other color up there. So AO would be R alpha, capital R, alpha I hat. Let me bring them down a little bit. I don't want to use the top of the. So AO equals to R alpha I. This is from half cylinder, the center of cylinder, the geometric center, the acceleration of A, because if there's no sliding condition, it would be R alpha. Because if we track if it goes by distance D and it traces that length, so let's say, for example, if it goes that much, then this, if there is no slipping, this would be this much, because point would come down to its corresponding point. So R theta equals to that X. So if we do double derivative of R theta, we get R alpha, because this is R theta, the arc length is R theta. And this is X, the amount that this goes in the X direction. The height is always constant. It is always at R, this center of half cylinder. So this X equals to R theta. So X dot equals to R theta dot, or R omega. X double dot, or acceleration, equals to R alpha, or R theta double dot. This is from geometry. Now we use the other equations from rigid body, kinematics of rigid body, and that is Eg, we can plus omega cross alpha cross OG. All right. This is zero because omega is zero. It said that it starts, it is initially at rest. So this is zero. So we would have R alpha I hat plus alpha is, we assume that this is the direction that we have alpha. So it is negative alpha K hat. Cross OG is R negative R J hat. So K hat cross J hat, it becomes negative I hat, and we have positive. So it would be R alpha I hat minus R alpha I hat. All right. So now, in other words, it is just R minus R alpha I hat. Now we see that there is no J hat. So this AY, which is the Y component of AG, is zero. This would be this one. And this, we can write it again. So we would have FF equals to M alpha R minus R, N minus MG minus F equals to M equals to zero. We saw that the Y component is zero. And then we have FR minus FF R minus R equals to I alpha. Now let's look at it again. We have FF as unknown, N unknown, and alpha. So we have three variables and three equations. So we should be able to solve it, right? So we see that FF, we can find FF in terms of alpha from here, replace it here, we find alpha. So we would have from this and that one, we get F R minus M alpha, then R minus R squared equals to, yeah, we just multiply that by that, equals to I alpha. So we bring alpha to one side, we bring that to that side, and we factor out alpha. So alpha equals to FR divided by I plus M R minus R squared. By the way, this I is around center of mass. So this is in fact IG, all right? So I use this as IG. This is IG is just I. Let's put it here. I just say that this is I. So we found alpha. And that's it. It is, I mean, everything is geometric value, and we know all of them, and F is given. So find the minimum value of mu S, the other part, such that there is no sliding. So always my FF is smaller than mu Sn. When we find the minimum value of mu S, it means that my FF is right at the sliding condition. So mu S is reduced. So we are saying again that FF is always smaller than mu N. So we reduce mu N, mu N, mu N such that we arrive at FF at that force. So they are equal at that moment. And we can't use mu S anymore because FF for no sliding should be always smaller or equal to mu Sn. So don't forget that the friction force is not always mu Sn. It is always smaller if there is no sliding. But when it is on the verge of a sliding, meaning that if we want to find the minimum value of mu S, or sometimes we want to find, for example, the maximum of F or the maximum of acceleration, either make this bigger, make this smaller. They are equal. So now we would say that FF equals to mu N. So we use this N equals to mg plus F, right? So now that we've, all right, let's use the rest of the space. So we find from here, we get that N equals to F plus mg. Then this is mu times this should be equals to FF. So we get M alpha R minus R, which is FF, should be mu N, should be F plus mg. So we found alpha already. I don't want to replace it there. So we would say mu equals M alpha times R minus R, whole thing, divided by F plus mg. So we found alpha already, we replace it there. And I mean, we can keep it that way because alpha is known now. So M alpha R minus R divided by F plus mg and everything. And this is the minimum of mu S. All right.